Welcome back to our final day of Chapter 5, ladies and gentlemen. We are on day 3 of Section 5.3, Conditional Probability and Independence, a special multiplication rule. All right, so by the end of this lesson, you'll be able to determine whether two events are independent, and also, when appropriate, you'll be able to use the multiplication rule for independent events to compute probabilities. As always, try this assignment after our lesson. Let's begin. So 5.3, day 3, multiplication rule for independent events. You can read much of this information on pages 372 to 375 in the updated 6th edition of the Practice of Statistics. What is the multiplication rule for independent events? Is it on the formula sheet, and how is it related to the general multiplication rule? So our definition, if A and B are independent events, the probability that A and B both occur is the probability of A and B, which is equal to this symbol language, is equal to the probability of A times the probability of B. Now, the thing to note is that if events A and B are independent, then the probability of B given A is equal to the probability of B. So the multiplication rule for independent events is just a general multiplication rule with probability of B given A replaced with probability of B using the substitution property. Right? This is replaced with probability of B because they are equal. Right? And how is this on the formula sheet? No, this is not on the formula sheet. However, it can be derived from the conditional probability formula if you know the definition of independence, just like the general multiplication rule can be derived from the conditional probability formula. All right, so both the multiplication rule for independent events and the general multiplication rule can be derived from the conditional probability formula. Now, if events are mutually exclusive, they cannot be independent because you already know that if the first event happened, the second event could not occur due to the definition of mutually exclusive events. So for example, if you choose a U.S. adult at random and know that the individual selected is a cisgender male, then the chance that this individual is pregnant is 0. Right? These events, being a cisgender male and being pregnant, are mutually exclusive. They also cannot be independent because the probability of a randomly chosen U.S. adult being pregnant is not 0. The condition we placed changed the basic probability, meaning that the two events are not independent. All right. Now, example 1. What is the probability of flipping heads on a coin and rolling a 6 on a fair die? So probability of heads and rolling a 6. Flipping a coin and rolling a die will not affect each other's results. Therefore, probability of heads being 1/2 and probability of a die landing with its 6 landing on a 6 is 1/2 times 1/6. Multiply those. When you multiply fractions, you multiply straight across. 1 times 1 is 1. 2 times 6 is 12. The probability is 1/12. You don't have to try to find a conditional probability because these two events are not conditional. They are independent. For example 2, the first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the developing baby. According to a study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will receive a false positive result. Among 100 women with normal pregnancies who get this test, what is the probability that there will be at least one false positive? Now, something to keep in mind, at least one false positive, you would need to find the probability of 1 false positive, 2 false positives, 3 false positives, all the way up through 100 false positives in order to be able to add all of those together. That is a nightmare situation. So we're going to use the complement rule. The probability of at least 1 is the complement of the probability of no false positives, which is much easier to calculate. So we're going to calculate the probability of no false positives and then take 1 minus that probability in order to calculate its complement. Now, probability of a false positive is 0.05, which means the probability of not a false positive is 0.95. The probability of no false positives in 100 tests of normal pregnancies would be the probability of no false positive and no false positive, and you're basically repeatedly finding the intersection of 100 events all at once. So instead of just 2 things multiplied, you're going to have to take the same probability multiplied onto itself 100 times. All right, so it says 0.95 times 0.95 times 0.95 100 times, and repeated multiplication by the same number, that's what exponents are for. That's the definition of an exponent. So we're going to take 0.95 to the 100th power, and when you put that into your calculator, you get 0.0059. Now, that was the probability of no false positives. We wanted at least one false positive. Let's make sure we actually answer our question. We still need to take 1 minus the probability we just found. So the probability of at least one false positive is equal to 1 minus the 0.0059 we just calculated, which is equal to 0.9941. That is our final answer. So sometimes you use the multiplication rule for independent events along with the complement rule to help you calculate really complex probabilities. And for our final example, on a recent day, WGN Weather forecast a 50% chance of rain in Aurora and a 50% chance of rain in Naperville. What is the probability that will rain in both locations? We actually cannot answer this question because the events are not independent. Right? The chance of rain in Aurora affects the chance of rain, the likelihood of rain in Naperville, and vice versa, because they're in the same sort of geographic location, so weather sweeps through them in a related manner. Right, so that is not a probability that we can calculate that it will rain in both locations. We don't have the information for that. Right? Please try this assignment, and I will see you in class.